So next topic is polymorphism. Let's talk about the core idea in object-oriented programming that you'll be using constantly from here on out, which is polymorphism. Uh, so polymorphism in simple words means many forms. So in practice, it's the ability to write the code on a parent type while letting the child classes decide what to do, what to actually do. So an example is, imagine I have a person class and then I have a employee class that extends person. So let me go back. So if I write this line, person P is equal to new employee Ava 0.0. So you'll notice something interesting here is the variable type is person, but the object we are actually creating is an employee. That's called upcasting, treating a more specific object as if it were just its parent. So now here's where the magic happens. If I call a method on p, like p.info, Java doesn't just look at the reference type, which is the person. It looks at the actual object in memory, which is an employee. So and it will run the employee version of info. That's called dynamic dispatch. The decision about which method to run is made at runtime, not at compile time. So why does this matter? Because uh, it means we can write code that doesn't need to know the exact type of object it's working with. For example, I can have a method that accepts like list person. Into that list I can add employee, student, manager, any subclass of person. And when I loop over the list and call the info uh, on each one, each object will automatically run its own version of the method. I don't have to write a giant if or switch statement to check what type it is. The code is reusable and flexible, and sometimes you do need to know exactly what type you're dealing with. That's where downcasting and the instance of operator come in. For example, if you really need to call a method that only exists in employee, like uh, calculate pay, uh, and your variable is typed as person, you might do something like this, like this one. So if p instance of employee and employee e equals employee and p system dot println e dot calculate pay. So that works. So here's a caution. You should use downcasting sparingly. The whole point of polymorphism is that your code should usually rely on parent type, not keep asking what are you really. and forcing cast. If you find yourself doing that a lot, it usually means your design should expose the behavior at the parent level, like making the calculate pay part of the person or employee abstraction. So the key takeaways here is upcasting lets us treat child objects as their parent type, and dynamic dispatch ensures the right version of the method runs based on the actual object. And polymorphism makes your code flexible, reusable, and downcasting with instance of is a tool, but it should be the exception, not the rule. So that's polymorphism. It's one of those concepts that feels abstract when you first hear it, but once you start coding with it, you'll see how much power it gives you in writing cleaner and smarter programs. um, next next we have array list of objects and supertypes. So let's move and talk about array list, not just with simple data types, but with objects and specifically with superclasses. Uh, so you already know that an array list is basically a resizable array. Unlike a plain array, you don't have to decide the size up front. You can just keep adding elements. Now the real power shows up when you combine the array list with polymorphism. So imagine we have a person class and subclasses like student, employee. If I make a uh, array list person, and I can add all kinds of objects into it: a student, an employee, uh, even a manager that extends the employee. And when I loop over that list, I can just call info for each one, and the right version runs for each object, and that's polymorphism in action. So the key difference here is uh, array list person versus array list object. Technically every class in Java extends object, so you could throw anything into array list object, but that's usually not what you want. If I store things in array list object, every time every time I pull something out, I have to cast it back to what I think it is, and that gets ugly fast. So with array list person, uh, the compiler knows every element is at least a person. That means no unsafe caches. You still get the benefit of polymorphism when you call methods that belong to class. So rule of thumb, use the most specific super type that actually makes sense. If you're working with people, make it list person. If you're working with shapes, make it list shape. Don't default to object unless you truly want to mix totally unrelated things. Let's talk Let's also talk quickly about iteration patterns. You can loop through array list by index. For example, let's write a for loop int I is equal to uh, I people size I plus plus system dot render and people dot get and dot info. So yeah, this is useful when you if you care about index, but most of the time the enhanced for loop is cleaner and easier. So like we could replace this with person p people, and just print ln, you'll just print p. So it's shorter, it avoids index mistakes, it makes intent clear. You just wait to you just you just want to visit every element. uh, One last warning is avoid raw types. If you ever see new array list without uh, okay, I'm just gonna without this one t part, that's a raw type. It turns off type checking, and suddenly you can mix in whatever you want, person, string, integer, and you won't find out it's a problem until runtime when something blows up. Always use generic form like array list. It's uh, array list, yeah, something like this. So to uh, sum it up, stick with super type stick with the array list super type instead of array list object. Iterate with the enhanced for loop unless you really need the index. Never use raw types. That's combination keeps your code clean, safe, and fully takes advantage of polymorphism. That's about. Next topic is abstract classes. So let's talk about abstract classes. This is the one of those topics that sound a little intimidating, but once you see the why and the how, it clicks pretty quickly. So what is a abstract class? Think of it like a blueprint that's not quite finished. It's a class you can't actually create objects from, but you can use it to set up shared state and behavior, and that all of its subclasses will inherit. And here's the key part: you can also mark certain methods as abstract. An abstract method just says what should exist, not what how it works. It's like a promise that every subclass has to fill in the details. For example, imagine we have an abstract class called shape. Every shape probably has things in common. Maybe a color field, maybe a method like move xy. Uh, that's shared code lives in the abstract class. But if we can, if we think about calculating the area of the shape, well, a circle does that differently than rectangle. So in shape, we'd write we'd write an abstract method like get area that tells Java, hey, any class that extends shape must provide its own version of method. Uh, so now because it's incomplete, you cannot create a plain shape object. You can't say new shape. Java won't let you. You have to create a subclass like circle, rectangle that actually implements the abstract methods. So why use abstract classes instead of interfaces? Uh, because interfaces are great for defining behavior like this thing can fly, this thing can be compared, but interfaces don't hold shared fields or partial code. uh, Abstract classes do. They let you put common data and even partial implementations in one place and then enforce that subclasses supply the missing pieces. So think of this way, use an interface when you just need a contract. Any class, like any class that says it's comparable, has to implement compare to. Use abstract class when you want to share code, and for subclasses to provide specific methods. uh, so to wrap it up, abstract classes give you a way to avoid rewriting the same code over and over, while still guaranteeing that certain methods exist in every subclass. They're not something you'll see every day, but when you hit the right design problem, like shapes, employees, or instruments, they'll make the code cleaner and easier to maintain. That's about abstract classes. Next, we have let's talk about one of the most important design ideas in object-oriented programming: is A versus has A. So here's the difference. When one class is a more specific version of another, you use inheritance with extends keyword. For example, a dog is an animal. That makes sense. So when one class just has a relationship with another, you use fields inside the class. That's composition. For example, a car has a has an engine. A car isn't just a type uh, of an engine, right? So it just contains one. So that's the difference. So the tricky part is knowing when to use which. Beginners often overuse inheritance because it feels powerful, but inheritance only works when the relationship is truly is a. If you find yourself saying, well, kind of it depends, then it's probably not real is a, and you should go with has a instead. So here's an example. Let's say you're modeling a car, so you might be tempted to write a class extends engine, but that doesn't make sense. A car isn't an engine. A car has an engine. So that's a right design. Uh, so class engine, that's it. Let's just put notes. And class car, let's open one. Private engine. This is basically car has a engine. And let's close this. So that's composition. The car has a engine field, and it can call methods on that engine, like engine.start. It can be anything. So now here's one principle that helps you decide, the Liskov Substitution Principle. So don't worry about the fancy name. In plain English, it just means this: if class B extends class A, then anywhere you use an A, you should be able to substitute B without breaking exceptions. So like so if a dog extends animal, you can put a dog anywhere you extend an animal. uh, it should still behave like an animal. That's good inheritance. So but if you made car extend engine, then everywhere you expect an engine, suddenly a car shows up. That doesn't really work. That's a bad is a relationship. So use is a, which is extends only when it's a true subtype. Use has a, which is composition, when one class owns or contains another. And always ask yourself, if I swap in the child for the parent, does it still make sense? If yes, it's probably is A. If no, stick with has A. So getting this right will make your designs way more natural and prevent headaches later on. Uh, so the last topic is UML. Uh, so that's UML, full form is Unified Modeling Language. I know the name sounds like something out of a textbook, but I'm gonna cover the bits you'll actually use in the course and in real world programming. So the most common diagram you'll run into is a class diagram. Think of it as a simple sketch that shows what a class looks like without writing full code. A class diagram has three parts stacked on top of each other. At the top, you'll see, for example, you'll see class name. In the middle, the fields, basically the data the class holds, and at the bottom, the methods, what the class can do. So if I drew a box for a person, it might say person at the top, then under that name, which is a string, age, it's an int, and then under that you'll like methods, get name, get age, which is get name is string, get age is int. So that's all there is to it. So how do we show relationships between classes? So first, inheritance. So if one class extends another, we draw a line with open triangle. I tried my best to put this in a PPT, but yeah. So if one class first inheritance, if one class extends another, we draw a line with open triangle arrowhead pointing to the parent. So if employee extends person, you draw a line from employee up to person with an open triangle on the person side. That's the standard inheritance arrow. Second is interfaces. So if a class extends an interface, you use basically the same arrow, but the line is dashed instead of solid. So if employee implements comparable, you draw dashed line with open triangle pointing to comparable. Next is we have composition, aggregation. These both show has a relationship, but with slightly different meaning. So here composition means strong ownership. If the parent is destroyed, the child goes with it. In UML, that's shown in a solid diamond. For example, a car has a engine. If car goes away, the engine isn't meaningful on its own. That's aggregation is a loser relationship. The child can exist on its own. That's shown with a hollow diamond. For example, a team has players. The team might be dissolved, but the players still exist as people. So yeah, that's it. Class boxes, arrows for inheritance and interfaces, and diamonds for has a relationship. If you can read and sketch those, you'll understand 90% of UML diagrams you'll ever actually encounter as a developer. The key is to treat UML like a quick sketch pad, just a way to communicate structure without writing full code. Don't worry about memorizing every symbol in the language. Focus on these basics. You'll be set. Uh, let's talk about the interfaces a bit. So uh, interfaces are one of those ideas that sounds scarier than they really are. So uh, at their core, an interface is just a contract for behavior. It says any class that implements me promises it will provide these methods. Uh, so unlike an abstract class, an interface doesn't hold state. You won't file normal instance fields inside. That's the only fields allowed are public, static, final constants, which are basically just global constants. So uh, in Java 8, interfaces got a little bit a little more flexible. They can actually include default methods and static methods. A default method is just an interface method that already has a body, so you can give a reasonable default behavior. uh, Classes, uh, so classes that implement the interface can use it as is or override it. Static methods, as usual, belong to interface itself, aren't tied to objects. So one of the biggest advantages of interfaces in Java is that a class can implement multiple interfaces. Uh, this is in uh, contrast to inheritance, where you only get to extend one class. So for example, a class might extend person but only implement comparable, iterable, and maybe even AutoCloseable if it manages resources. That's how Java lets you mix different capabilities without running into the problems of multiple inheritance. Uh, Let me give you a couple of common examples you'll run into uh, all the time. Um, so first is comparable. So basically this lets objects be compared, like sorting employees by ID or books by title. We have iterable. This makes your class work with enhanced for loop, like for each. Uh, and we have auto closable. This is for classes that manages resources like files or database connections, or so you can use them in a try with resources block and have them close automatically. So in short, interfaces contracts for behavior. They don't carry normal fields, but since Java 8 can have default and static methods, you can you can implement as many as you need, even while extending just one class. And the built-in ones like comparable, iterable, autoclosable show all over the place. The key takeaway is that interfaces let you add capabilities to your classes without messing up your inheritance chain. They are one of the main tools in Java to keep code flexible and reusable. Uh, yeah, that's all for chapter 11, inheritance.